Good morning, Professor. Today our group will present our Goalless 2 project, designing the most cost-efficient beverage can. Let's take a look at the standard beverage can. It seems like a simple object, but billions of these are produced globally every year. In manufacturing, even a fraction of a millimeter reduction in aluminum usage per can translates into millions of dollars in material savings for a company. Furthermore, using less material using mass material means lighter shipping weights reduce fuel consumption and a smaller carbon footprint, therefore determining the optimal shape that minimizes surface area while holding a specific volume of liquid is critical engineering and business challenge. Our primary objective today is to find this optimal shape to minimize production cost, since the cost of a can is directly proportional to the amount of aluminum used. Our practical goal translates mathematically to minimizing the total surface area of the can, subject to the constraint of a fixed volume. However, before we apply multivariable calculus to solve this, we must establish a clear mathematical model. Real-world objects have complex variations, so we need to set specific core assumptions to make this problem solvable using the optimization tools that we have learned. First, we assume the beverage can is a perfect cylinder. We assume the can is a perfect right circular cylinder. We will ignore the indentations at the bottom, the sloping at the top, and the pull-tab mechanism. Second, we assume uniform material thickness. We treat the top, bottom, and sides as having the exact same thickness and costing the same amount per square centimeter. In reality, the top lid is often thicker to withstand internal gas pressure, but for our baseline model, the cost function remains uniform across the entire surface. Third, we assume zero material waste during the manufacturing process. The cost is calculated strictly based on the final geometric surface area of the cylinder, ignoring the scrap metal left over from cutting circular tops from rectangular aluminum sheets. By establishing these parameters, we successfully transform a complex manufacturing issue into a precise multivariable optimization problem. In the next section, my teammate will guide you through the Goalless 2 concepts we use to solve this, specifically focusing on Marshall derivatives and constraint equations. And that's all.
My name is Henry Tao. My student ID is 6025090007. Now let's move to part 2, Goalless 2 review and modeling. In this section, we will convert the physical geometry of beverage cans into multivariable functions and introduce the Lagrange multipliers method. First, let's review the key calculus concept. Lagrange multipliers. This method is used for optimization under constraint. As shown on the slide, if we want to minimize a function with a fixed constraint, we apply the Lagrange multipliers we learned in Calculus 2. At the optimum dimensions, the gradient vector of our objective function, total surface area, and the gradient vector of our constraint function, volume, are parallel to each other. We introduce a scalar multiplier named lambda. Then we take partial derivatives with respect to radius and height, which forms a system of equations for us to solve. Next, the we formulate our mathematical model, which has two parts, the volume constraint and the cost objective function. The first part is our constraint for volume. A beverage must hold a fixed amount of liquid, such as 330 millimeters or cubic centimeters. The volume of a cylinder depends on its radius and height, written as this formula. This volume values stay constant and throughout our calculation. The second part is our objective function, which represents product cost. Materials cost is directly proportional to the can's surface area. So our goal is to minimize the total surface area. So this formula covers the lateral side wall and two circular top and bottom ends of the cylinder. With our mathematical models fully built, we will apply these formulas to the 330 millimeters beverage can and calculate the optimal size in part 3.
Hello everyone, now let's talk about part 3, about case study and optimization. Applying our mathematical model to solve for a standard 330 ml beverage can. First, solving the system of equations, we need this H equals to 2R, the golden ratio of cans, and we need two steps to solve this. First step is compute gradients. We use the equations we learned from class to estimate it to solve these problems. And step 2, solve for lambda. From the second equation, simplifying yields lambda equals to R delete R. Substituting this back into the first equation, and therefore to minimize surface area, the height you must use is get equal the diameter. Now, let's talk about the exact question. The 330 ml can. We plug our phase volume V equals to 3030 into the formula to calculate the exact theoretical size. The optimal radius R equals the cube root of 3030 divided by 2 pi, which gives us R equals to 3.74 cm and H equals to 7.42 cm. Under these dimensions, the total surface area is only 264.4. The smallest possible material usage for a 3030 ml can. Now let's look at the comparison table on the slide. We put our theoretical optimals can side by side with a standard commercial soda can you can buy in supermarkets. The real can has a smallest radius of 3.30 cm and a much taller height of 11.52. With a height to diameter ratio of 1.74 instead of 1. This total surface area rises to 307.2, which uses around 16% more aluminum than our mathematical ideal model. And this focuses on a very difficult situation.
Hello everyone. In the previous part, we found the mathematical perfect can. It has a height equal to a diameter. But if you look at a real soda can on a supermarket shelf, it looks taller and narrower. Why is that? In this final part, we will explain why real-world engineering often moves away from pure maths. First, let's talk about our biggest mistake in the model. We assumed the aluminum was the same thickness everywhere, but this is not true in real life. In a real beverage can, The top and bottom are much thicker than the sidewall. In fact, they can be 2 to 3 times thicker. Why? Because the drink inside is under high pressure from carbonation. The top and bottom needs extra strength to stop the can from bursting. So, when we update our mat to account for this, we give more weight to the top and bottom areas. The new optimization problem changes. Now, the bed shape is no longer a short wide cylinder. Instead, it becomes taller and narrower. This new shape is actually what we see on store shelves. So, the real can is not wasteful. It is optimized for a different cost structure. Second, there are human factors. A can isn't just a container. It's a product that people hold. A taller, narrower can feels much more comfortable in our hands. Think about it. Can you easily hold a short fat can? Probably not. Also, this taller can fit perfectly into standard car cup holders. This is very important for customers who drink on the go. Third, we have to think about packing and shaping. Cylinders don't pack perfectly together. This is always some empty space between them. However, a taller can make better use of vertical space. On retail shelves and in shipping boxes, height matters. By making the can taller, companies can pack more product into the same volume. This saves money on transportation and shelf space. Finally, this is marketing. Research shows the consumer often think taller containers hold more liquid, even if they actually contain the same amount. A tall slim can looks more modern and premium. It catches the eyes on the shelf. So the design isn't just about saving materials. It is also about selling more drinks.